A wind turbine appears tranquil at first glance, with its three slender blades rotating in a slow, hypnotic rhythm, suspended high above the landscape. However, the graceful motion conceals a modern engineering achievement. Complex systems housed over 100 meters in the sky are utilized to generate clean energy by wind turbines, which are among the most advanced and demanding devices on Earth. This comprehensive article will provide a detailed explanation of the operation of a wind turbine, the methods by which technicians access these machines for maintenance, and the experience of working in the high altitudes where the wind is turbulent, the space is limited, and each maneuver necessitates precision. This is your insider's guide to turbine tech and operations, whether you are a budding wind technologist or simply captivated by renewable energy. The mechanism of a wind turbine, the inside of the machine that converts air into electricity. Wind turbines utilize a series of precisely calibrated processes to convert the kinetic energy of the wind into electrical power. The rotor, nacelle, transmission, generator, and tower are the 5 primary components of each turbine. Although animated schematics are beneficial for comprehending the process, real-world footage from the field showcases the grime, the motion, and the roar of the machinery that seldom rests. It all commences with the rotor, which is composed of 3 long aerodynamic blades that are connected to a central center. The turbine is spun by the blades, which are meticulously designed to capture the wind. The rotation is subsequently transferred to the main shaft, which extends into the nacelle, the substantial structure that sits atop the tower and houses the system's heart. The blade's sluggish rotational motion must be significantly enhanced within the nacelle. That's where the gearbox comes in. To operate efficiently, electricity generators necessitate thousands of RPM, while a typical turbine blade rotates at approximately 10 to 20 RPM revolutions per minute. The speed is multiplied by the transmission, which transfers the amplified rotation to the generator through a system of planetary gears. The generator functions similarly to a substantial alternator. Alternating current AC electricity is generated through the application of electromagnetic induction. This electricity is then transmitted through thick cables that are located within the tower. The electricity is frequently converted to direct current DC or optimized to align with the local electrical frequency before reaching the grid, where it passes through transformers. Additionally, these systems are equipped with yaw motors to rotate the nacelle and align it with the wind, braking systems to prevent the turbine from operating in the event of an emergency or overspeed, and control units that continuously monitor hundreds of data points, including wind direction, temperature, torque, and vibration. Turbines are now equipped with lightning protection systems, fire detection, and even dehumidifiers within the nacelle to prevent electrical malfunctions in severe environments. It is not merely a substantial fan, it is a miniature power plant mounted on a pole. A comparison of access methods. The methods by which technicians access the sky. Turbine maintenance necessitates more than mere comprehension of their operation. It necessitates the ability to access them safely and efficiently. Various access methods may be employed by technicians, contingent upon the turbine's location, size, and the mission at hand. The hazards, costs, and physical demands of each method are distinct. Platform lifts, internal lifts, which are comparable to industrial elevators, are included in certain contemporary wind turbines. These lifts facilitate the transportation of technicians from the base of the tower to the nacelle. Although these elevators are convenient, they are frequently slow and have a limited capacity. Additionally, they necessitate secondary safety systems and may be rendered inoperable during maintenance or power outages. Technicians are typically required to climb the last 5 to 10 meters using vertical ladders, all while donning fall arrest systems, even with a lift. Lifts are a comfortable option. However, they are not a universal solution, as many older or lesser turbines lack them. Crane access. Crane access is indispensable when weighty components, such as gearboxes or blades, require replacement. Massive crawler or telescopic cranes are transported to the site, necessitating several days to construct. The crane is capable of lifting technicians in man baskets or handling blade sections and nacelle parts that weigh several tons once it is operative. The cranes provide precision and stability. However, they are not without their drawbacks. Particularly in remote regions, they are exceedingly costly to implement. Operations may be entirely suspended due to weather conditions such as lightning or high winds. Additionally, crane access is challenging in rugged or offshore terrain due to the extensive space required for setup. Rope access. For blade inspections and minor repairs, rope access has emerged as the preferred method due to its cost-effectiveness, rapidity, and flexibility. Using equipment adapted from alpine climbing and caving, certified rope technicians rappel down turbine blades while carrying composite tools and epoxy in backpacks. The advantages are evident. Rope access necessitates minimal apparatus, very little space, and no cranes. It is optimal for the examination of surface damage, erosion, and fractures. Nevertheless, rope access necessitates perpetual adherence to safety protocols, exceptional physical fitness, and rigorous training. The technicians are frequently working in strong winds, hundreds of feet in the air, with only a few millimeters of rope separating them from the earth. Each technique has its appropriate application. Platforms are optimal for internal examinations. The utilization of cranes is essential for significant restorations. However, rope access continues to be unparalleled in terms of speed and adaptability for the daily routine of blade maintenance. A first-hand account of the experience of working on a 100-meter turbine. Imagine waking up before sunrise, loading your equipment into a four-wheel drive vehicle, and driving into vast open fields where wind turbines tower like white titans from the earth. The wind is consistent. The temperature is either extremely hot or bitterly frigid. Today, your office is situated 100 meters above the earth. Climbing a wind turbine is an endurance test. Despite the use of a lift, the harness, helmet, hydration system, and tools weigh between 10 and 15 kilograms. A metal ladder ascends within the structure, resembling a scene from a science fiction film. You pause at rest platforms every 20 to 30 meters to recover your breath, wipe the sweat from your brow, and listen to the tower creak in the breeze. The sensation of entering the nacelle is akin to that of entering a spacecraft. It is a noisy device with mechanical whirs, electronic sounds, and the wind pounding against the shell. You promptly secure your fall protection lanyard to the anchor points. Grease, resin, and heat emanate from the atmosphere. Some technicians experience claustrophobia in enclosed areas. Others find it exhilarating. The genuine challenge arises when operating outside the nacelle, such as on the top of a blade. Standing on the turbine roof, with only a tether attached to a rail, you are afforded an extraordinary view. Miles of land extending in all directions, clouds afloat at eye level, and birds soaring on the same winds that propel your turbine. Rope access is utilized to enhance the experience of working on blades. You are reliant on your rigging companion for communication and backup while suspended beside a 50-meter blade in a full-body harness, buffeted by gusts. The task is demanding, grinding away damaged fiberglass, applying resin, sanding, and waiting for the materials to cure. It is a mentally concentrated, physically demanding job in which each error has the potential to be either costly or dangerous. Breaks are exceedingly uncommon. Lunch is consumed in brief intervals, frequently consisting of a protein bar and water, while the individual is seated within the nacelle or crouching on a maintenance platform. Radio communication is the primary method of communication with the ground personnel. If weather conditions change, you may be compelled to halt and descend promptly. However, it possesses an unusual attractiveness. This occupation is unparalleled due to its isolation, significance, and adrenaline rush. You are not confined to a cubicle. Standing in the heavens, you are. Conclusion: the future is in motion. Wind turbines are no longer futuristic concepts. They serve as the foundation of renewable energy systems that extend from Texas to the North Sea. The demand for qualified technicians has never been greater as these machines continue to expand in size and power, with blades that now extend beyond 100 meters. A more profound understanding of the tough, technical, and frequently invisible labor that sustains the green energy movement is facilitated by an understanding of the operation of turbines, the safe access to them, and the experience of working on them. Regardless of whether you are an engineer who is developing more intelligent nacelles, a technician who is grinding away blade damage from 90 meters in the air, or an individual who is merely inquisitive about the process of generating clean energy. It is important to remember that the wind is not the sole source of power for each spin of those massive blades. Rather, it is the minds, hands, and courage of human beings. Additionally, they are only beginning. If you enjoyed this video, don't forget to like, subscribe, and drop a comment below. We'd love to hear from you.